So today I'm going to start lecture 31, and here we are going to discuss the simplex method, which is widely used in linear programming, and I'm Dr. Ranjan Ganguly. Now the simplex method starts with one solution and then it keeps moving from one solution to the next, and the aim here is to continuously decrease the cost function until a minimum is reached. And this method is based on a geometrical figure or object known as the simplex. A simplex in a 2D plane is formed by any 3 points that do not lie on a straight line. If you go to a 3D space, then it is formed by 4 points that do not lie on the same plane. So if you think geometrically, figures such as the triangle or things such as the pyramid represent a simplex in the 2D and 3D space. Now if we extend this concept to n-dimensional space, a simplex becomes a convex hull of points which do not lie on one hyperplane. So essentially we have extended the concept from a plane to a hyperplane. A convex hull of points is the smallest convex set containing all the points. A simplex represents a convex set, which we have seen before also. And one of the things which is important in creating the simplex method is the concept of canonical form of equations. So let us consider a set of simultaneous equations of the form ax equal b, where we have a m by n system and rank A is m. Now this set of equations is said to be in canonical form if each equation has a variable with unit coefficient that does not come into any of the different equations. So this will become very clear in the next slide. So here you can see a typical canonical form. As you can see here, the variable x1, which is there in the first equation, equation 1, is not present in the remaining equations. Similarly, the variable x2, which is there in the second equation, is not present in the remaining equations, and all the way to xm. So all these x1 to xm have a unit coefficient, and the remaining xm plus 1 to xn have certain coefficients given by this letter a. So x1 is there in the first equation, x2 is there in the second equation, xm is there in the mth equation. Now we typically do not want to write out this whole equation set every time, so we create a matrix form for this set. And so I can write this as I into xm plus q xn minus m equals b. So this is basically the set of simultaneous equations written in this form. And you can immediately start seeing the applications of this to the linear programming problem. So basically, again, this is the equation. Here I is an m by n, m by m unit matrix, and you have xm vector and you have a xn minus m vector. So these are the two vectors. Now you clearly recall that these represents the basic variables and the non-basic variables. Now this Q matrix contains coefficients of the variables xm plus 1 to xn, and b is m into 1 vector. Now typically a numerical method known as Gauss-Jordan method is used to convert a given system of equations into the canonical form, and the canonical form facilitates the calculation of basic solutions. So how do you get the basic solution? If you look at this equation here, if I set the non-basic variables to 0, then xm equals b gives the basic solution. So essentially, again, recall that the non-basic variables are classified as null. So xn minus m, I set them equal to 0, and therefore xm becomes b, which is the basic solution. So the canonical form is also represented as a tableau, which lets you do a systematic determination of the basic solutions. And the tableau can be used to solve simple problems manually, which you can see in books, and do various solved examples to get a feel of this method. So again, the whole objective of putting this problem in canonical form was to get the basic solution in a very simple manner. Now, this is the canonical form written out as a typical tableau. So you can see the correlation between this matrix equation here and this equation or this tableau here. And you can see that x1 to xm are the basic variables, and the xm plus 1 to xn are the non-basic variables, and the right hand side are the coefficients b1 to bm. Now, we saw in a previous lecture that we can find all the basic feasible solutions and compare them to get the best point. But we also discussed that this is possible for simple problems with 6, 10, or 20 design variables. But if you have thousands, if not millions of design variables, then the LP problem is essentially gargantuan or extremely large. And so investigating all the basic feasible solutions is extremely computationally expensive and difficult. And therefore we need a better method so that we don't have to search all the possible basic feasible solution. And that's something which the simplex method tries to do. So a simplex method is a faster way of finding the basic feasible solutions. So here we start with the basic feasible solution at one of the vertices of the convex polyhedron. And then we move to a new point such that there is a greatest decrease in the objective function. The simplex method is much more efficient than the brute force approach of searching for all the basic feasible solutions. So the simplex method starts from a basic feasible solution, and the simplex method finds out which current non-basic variable should become basic. And the simplex method also points out which current basic variable should be made non-basic. So this particular transition is governed by the theory behind the simplex method. Now the Gauss-Jordan method, which is a numerical method, is used to change the basic to the non-basic variables and vice versa. And there is a step known as the pivot step, which is a key component of the simplex method. The pivot step is used to replace a current basic variable with a non-basic variable to search for the best basic feasible solution. Now this pivot step would require you to select a basic variable xp, where p ranges from 1 to m, to replace a non-basic variable xq, where q ranges from n minus m to n. Now the pth basic column is changed with the qth non-basic column, and this pivot step is possible when the pivot coefficient apq is not 0, because we need to divide by apq in some of the equations we will consider next. So one of the requirements is that apq should not be equal to 0. So following this pivot step, xq will become basic, and it is essentially removed from all the equations except the pth equation. And again, this can be done by performing a Gauss-Jordan step on the qth column of the tableau using the pth row for removal. This will give you apq equal 1 and zeros in all the remaining places in the qth column. The row which is used for this removal process, which is the pth row, is called the pivot row, and the column on which this removal is performed, which is the qth column, is known as the pivot column. The process of changing a basic variable with a non-basic variable is also known as a pivot step. Now let us say that a-ij denotes the new coefficients in the canonical form after the pivot step. Then there are a series of expressions which can be used in the pivot step. So APJ dash would be APJ by APQ, where J is varying from 1 to n across all the design variables. BP dash is BP by APQ. So we are simply dividing these by PQ. But in the cases where I is not equal to P, we have to use these expressions here, which is Aij dash equals Aij minus APJ by APQ into AIQ. And here I is not equal to P, I is equal to 1 to M, J is equal to 1 to N. So remember, you are dealing with M by N system here. Similarly, Bi dash becomes Bi minus Bp by APQ into AIQ. For I not equal to P, I is 1 to M. So these will give you the new values of these particular coefficients once the pivot step is done. Now we'll look at some of the logic behind the simplex method in converting the basic variables and the non-basic variables. So let us first consider the case of a basic variable to be made non-basic. So let us say we have the canonical form, and xr is a non-basic variable which has been selected to become basic. Then the non-basic column corresponding to this r should replace some current basic column. So what we do in the canonical form is that we move all the values which correspond to xr to the right hand side in the canonical form. So remember that xr is a non-basic variable, so it is going to be one of these variables for which coefficients are there, and therefore I can take a1 comma rxr from this set and move it to the right hand side. Similarly, in the second case, I can take a2 comma rxr and move it to the right hand side, and all the way for the row number m, I can take amr xr and move it to the right hand side. So by doing this, I put all these terms related to xr to the right hand side. Now, one of the things which should happen is that since xr is to become a basic variable, its value must become non-negative. So this is going to act as one of the foundations behind how we select the next point. So we can see that if xr became too large, some of the right hand parameters bi minus airxr shall become negative, because this coefficient may become negative here. Now the right hand side parameters are the new values of the basic variables. So this would violate the non-negative constraints which are there, and the new basic solution will not be feasible. Thus we come to a requirement that these bi minus air xr must be greater than equal to 0 for I1 to m. Now two cases are possible in this case. The first case is if the air is less than 0, then of course air xr is less than equal to 0 since xr is greater than 0. So this is not a problem. However, if air is greater than 0, xr can be increased from 0 until one of the inequalities, say the one corresponding to r equal to s, becomes active. So at that point, bs minus asrxr equal to 0. So what we have done here is we have taken this particular expression where r was there, and we have said that at certain point s, this particular thing is going to happen, and therefore this equation is going to hold here. Now if you further increase xr, that will violate the non-negativity constraints. Thus the maximum value of xr would be bs by asr would be, you take all these ratios of bi with positive air and select the index with the least ratio. So this is something which we need to do, and since in all these cases air is greater than 0, the theory which we have discussed before would apply. Now there could be a situation where all these airs are less than 0, and in that case xr could be increased without any bound. Such a situation could happen if the LP problem is unbounded and the problem formulation needs to be examined in those cases. So there may be something wrong with the problem formulation. Now there's also the possibility that two variables are equal, then whichever one of the indices can be selected as S. The resulting feasible solution may be degenerate, which means that a basic variable is 0. The second key issue in the simplex method involves the selection of a non-basic variable which should be made basic. We want to bring a non-basic variable into the basic set to reduce the current value of the cost function. So what we do here is that we write the cost function in terms of only non-basic variables using the canonical form. So we take xi is bi minus all the non-basic variables. Recall non-basic variables range from m plus 1 to n. And so this becomes the cost function, or this becomes the value of xi from I is 1 to m expressed in terms of the non-basic variables. So our aim in this whole thing is to get this expression and then to plug it in the cost function. So the cost function was I is equal to 1 to n ci xi, and here all the xi were used, and now I can plug in these xi here, so I will be able to express this cost function only in terms of the non-basic variable. So here I plug this in here, and then you have to do some mathematics, and you can prove that f is f0 plus this equation here, where cj dash are these particular coefficients. Now of course for the bi term it is very simple to see. If I plug this here, then I would get bi ci term, and for the remaining part you can just do this by hand and you can get this expression here. Now this particular cj dash is known as the reduced cost function, and it essentially depends on the cj here and some of the coefficient. So here cj dash is the cost function of non-basic variables and is called the reduced cost function. So in general cj dash may be positive, negative, or 0. Let one of these cj dash be negative. Then the cost function will decrease since xj is greater than 0, and therefore this cj dash into xj will be less than 0. So xj is positive, so if cj dash is negative, this is negative, and therefore this is going to decrease the cost function because this term cj dash xj is going to be negative. Now the maximum decrease of the cost function will take place when you take the largest cj dash in the negative sense. So the largest negative value should be selected, and then you will get the maximum decrease in the cost function at the next possible point. Thus, if you take all these cj dashes ranging from m plus 1 to n, remember that these are non-basic variables. If any of these cj dashes is negative, then it is possible to find a new basic feasible solution that will further reduce the cost function. So that is the main thing which is coming out of this particular thinking. But if any of these cj dashes are 0, then the corresponding non-basic variable can be made basic without affecting the cost function. So that's something which is also possible. Also, if cj dash is greater than 0, then it is not possible to reduce f to any further point. Now this could be a situation where the current solution has come to the optimal point. So with all this theory behind us, we can now state the algorithm, which is the simplex method. So we start with a basic feasible solution obtained using the canonical form. So this is something which is required to start off this method. Express the cost function in terms of non-basic variables only. So we saw how this can be done. Now if all the reduced cost coefficients for non-basic variables are non-negative, that is the cj dash values, we have the optimal solution. So again, I think I may have mentioned cj dash as cost function in some place, but it's actually cost coefficient. So the fact is that all those cj dashes for non-basic variables, if they are non-negative, then there's nothing much we can do. But if any of those Cj dashes is negative, then we can find the pivot column. If all the values in this pivot column are negative, then the problem is unbounded. If there are positive values in the pivot column, then we take the ratio of the right hand side with the positive values in the pivot column and find the row with the smallest ratio. Then we complete the pivot step using the procedure and find the basic and non-basic variables and their values using the new canonical form. Calculate the cost function and again go back to bullet 3 in the previous slide and then continue this particular process till you get a final optimal point. So what you can see here is that the simplex method essentially uses a couple of steps to move in the right direction, or we should say move in the right manner in the design space such that the objective function value keeps coming down to the greatest possible extent. And through this process, the simplex method is able to get to the optimal point in a relatively fast manner compared to if you were to calculate all the basic feasible solutions and try to get the optimal point. So that is the main thinking behind the simplex method. And if you are more interested in details about the simplex method, you can refer to my book and also different books on this topic. So again, in my book, I provide several solved examples for the simplex method, which you can take a look at. So once you use this approach to solve a problem and you use the approach of the method of taking all the basic feasible solutions to find the problem, you will realize how efficient the simplex method is, and the efficiency becomes particularly greater as you go to problems of larger size. So that is something which is very important because in many fields such as chemical engineering, business management, supply chain, and so on, you encounter large linear programming problems. And so in those cases, simplex method may be a good method to use, though there are faster methods like the Karmakar's algorithm and so on, which one can use also. So again, in real world situations, various softwares are used to solve this problem, and you will find such softwares have been already developed and coded in by people. And then if you are doing a problem where you essentially need to solve a linear program for some practical problem, then you can use these software packages. But also if you are working in a class or trying to self-study, you can write a code on the simplex method using some of the things outlined in this chapter and then use it to solve the problems and check it with the solved examples which are given in the book. So again, that culminates lecture 31, and I will be back with lecture 32 on the further problems involving the simplex method and linear programming.